Hello, and welcome to our now fourth lecture for CHY 113. And we are now getting into the little bit more of the meat of the semester, both in this class, and you're probably finding that in your other classes as well. And so I just wanted to pause briefly to say that I think things so far have been going fairly smoothly in this course. Been a couple of small bumps that I've addressed with some of you individually. But I think overall things are going fairly well in this transition to teaching an online chemistry course. Like I think I mentioned in probably the course intro video, it definitely is not our preferred way to teach chemistry, but it's what we have for now, and I think everyone is transitioning to that fairly smoothly, and so I think things are going well so far. And so I wanted to start today just by reiterating some things that were in an email I sent out last week regarding ways to be successful in this course. And so I start out today with our course schedule up here. And so last time on Tuesday, I had posted our lecture on atomic structure. Today we're going to move on, and this lecture 4 will be posted right here by the time you're watching this. And focusing in on ions and how we name compounds and how we write chemical formulas. And so just a reminder that as you are looking at the schedule, so we're in this week right here, we're in the week of September 7th. And this was the topic that was covered in the last lecture, and here's the readings that you should have done hopefully ahead of time before you even saw that lecture. And now for this week, for this lecture that we're posting, here's the topic, and I'll click on this in just a second. But again, the readings that you should be doing, these sections within your textbook. And so hopefully you've read those and you've looked through that before you're watching this lecture. That really is the best way to succeed and to start to master the content, is by becoming familiar with the material before I even lecture on it, getting an idea of what is happening before we talk about it. And just this is the same recommendation that I would give if we were in a live lecture. If this were a traditional class format where you were coming to see me twice a week, I would absolutely be recommending that you are reading those sections before you come to lecture. And so this is no different here. The only difference is that you're watching me on a screen as opposed to watching me run around in front of you in the big lecture hall. And so hopefully you've done this reading here. Hopefully you've read and looked through these sections. And so then if we click on the topic here, remember that will bring you directly to the unit objectives for what we're going to be talking about. And we see from the schedule that we're focusing today on objectives 4 and 5. And so we scroll down to objectives 4 and 5. So we're going to look at how we can interpret, predict, and write formulas for ionic and molecular compounds, and the basic tasks for that. And so recall that if you click on the reading sections, it does bring you right to the appropriate sections in your textbook. And then the course video, molecules and ionic compounds. These are supplemental videos that I had created over the last couple of years that break the material down into slightly smaller chunks. And so sometimes it's a little bit more digestible to look at the material and to watch those videos, because they do cover less content than I will cover in the scope of this entire lecture. And then you'll see sometimes things in these in these unit objectives that you have to memorize. Memorization is just a fact of some of the things that we study in this course. And so in this unit, you should be memorizing the names, charges, and formulas of all of the common polyatomic ions. And we'll talk about those a little later in the lecture. This just gives you an idea of what you should be doing to succeed and to master the content in this unit. And you should also be memorizing the names and formulas of very common molecular compounds, such as water, methane, and ammonia. And then upon successful completion of this objective, you should be able to do all of these things. These things here, this successful completion, those essentially make up a study guide for an exam. I won't be giving out exam study guides. These are your study guides at the end of these unit objectives. So as you're getting ready to prepare for our first test in a couple of weeks, you should be focusing in on these things here under each objective. See if you can symbolize the composition of molecules using molecular and empirical formulas. Make sure that you know what empirical and molecular formulas are. Some examples, how we derive them. Make sure that you can derive ionic and molecular compounds or define them. What are they? Determining formulas. If you can do those things, if you read through that and you say, yeah, I'm really confident I can determine a formula for a simple ionic compound, then that's something that you would not want to focus on in your study. However, as you see down in objective 5, if you get to starting to prepare for the exam and you realize that, geez, I really have trouble naming compounds, I have trouble deriving names for some of these compounds using the approach, then those are the areas that you want to go back and focus on. So these essentially, these upon successful completion topics, those make up the study guides for your exam. Those are the things that you should really be focusing on as you prepare for a test. And those would be things to go back and look at even before you start really preparing for an exam. For example, early next week, I would go back and look at these. At that point, you've interacted with the material quite a bit. You've done the homework that goes over these topics. And so go back and look at them next week and ask yourself how comfortable you are with some of that material. And if you engage in that ongoing process of really going back and looking at your learning and thinking about, have I mastered this content that we have covered? And if you're making that an ongoing process rather than just covering it and then study for an exam later on, if it's really part of a big process that you're being very systematic about, you'll have a lot more success in this class. So just keep some of those things in mind as we go on, and especially as the material gets harder. To be quite honest, the stuff that we're doing in the beginning is the easy stuff. This class is going to get more difficult, substantially so. And so if you get into some of these habits of learning and studying early on, you will really be doing yourself a pretty big favor. And so with that being said, let's dive into today's material. Just move this and let's get going. Oh, starting a little ahead of myself there. I was looking ahead. Let's just go back. Okay, we're zipping through that. We'll be going over all of that stuff. Okay, so we ended last time looking at some of the regions in the periodic table. And we're going to need to be familiar with these regions when we move on with the things that we talk about today, especially as we look at the separation of the left-hand side of the periodic table. And when I say left-hand, I mean everything here in blue that I'm sort of circling with my pointer. Those are all metals. Everything over there is, from a chemical perspective, we call it a metal. And then we have this little transition zone here that we call metalloids, which have properties sort of in between metals. And over here in the periodic table, on the right-hand side in yellow, those are all of our nonmetals. It is important to note that hydrogen over here on the left is on the left, and it is in the section that we would consider to be metals. However, hydrogen is a nonmetal. When we start to discuss electron arrangements in a few weeks and really look in detail at how electrons are organized outside the nucleus, we'll see why we place hydrogen where we do. But note that hydrogen absolutely is a non-metal. Everything else over here, though, on the left-hand side of the periodic table is a metal, and our non-metals here. In most tables that you see and that you use, you'll see a differentiation there of some sort. This colored table, we can see that our metalloids here in light blue, and then we've got our separation. In other tables, see if I can find one here. Okay, just had to pause so I could find my black and white copy. In other tables, such as this one, you might not see that differentiation. And so it is going to be important for you to note, just as we move on through the class, that where our metalloids are. And so they're sort of in this staircase in through here. So boron, silicon, germanium, arsenic, antimony, and tellurium, and sort of right through here. And then again, everything to the left, metals, and everything to the right are nonmetals. And so that differentiation between the two, that knowing, being able to look at the position of an element in the periodic table and know whether it is a metal or a non-metal, that's going to be very important for us in talking about a lot of what we talk about today, in seeing how we name chemical compounds and how we come up with their formulas. And so if you haven't really keyed in on this and looked at this differentiation yet, be sure that you do, because this is a very important differentiation for us to know. Okay. And so as we define a couple things, and we looked at these definitions, I think, a little bit in the last lecture as well. A compound is just any combination of two or more elements that are in a definite ratio. And so something like H2O, everyone's familiar with the compound H2O. That's just our chemical formula for water. It means that every individual water molecule, so every individual molecule of water, is made up of 2 hydrogen atoms and 1 oxygen atom. And so a compound is just what we're saying, that's what water is. Water is a compound because it is made up of 2 or more elements. If we're talking about individual water particles, so to speak, then each of those individual particles are a molecule. Now we have 2 different types of compounds that we're going to be talking about in this class. We have ionic compounds, which are made up of a metal and a non-metal combination. That's going to be a very important combination that we see going forward. Or we have some sort of combination of a metal and a polyatomic ion, or in one particular case, a polyatomic ion and some non-metals. But by and large, what we're talking about here quite often are metal-non-metal combinations or metal polyatomic ion combinations. And we'll talk about what those are in a little bit. We also have what we call molecular compounds. A molecular compound is when a non-metal and a non-metal come together. And so something like, let's pull the periodic table back up here, something like H2O, something like water. Remember that hydrogen, even though it is over here, is a non-metal. Oxygen is over in our non-metal region of the periodic table. And so H2O is something we would consider to be a molecular compound. It's made up of 2 non-metals. Glucose. Remember back to your high school biology, our chemical formula of glucose, C6H12O6. Carbon's a non-metal. Hydrogen's a non-metal. Oxygen's a non-metal. And so glucose is something that we would consider to be a molecular compound. It's made up of non-metals. You'll also hear the term covalent compound, and that's the other type of bonding, which we'll talk about in a little bit. We have ionic bonding versus covalent bonding. And so covalent bonding is going to be when non-metals are coming together. And so something like the glucose that we talked about. Let's say we have NaCl, common table salt, sodium chloride. Sodium is a metal over here in our metals section of the table. Chlorine is a non-metal, so that's going to be an ionic compound. Or maybe, any other combination. Magnesium nitride. Magnesium is a metal, nitrogen is a non-metal, and so the 2 of them come together in an ionic compound. And don't worry about the ide, nitride and chloride and so on. We'll talk about those naming conventions later in this lecture. And so 2 different types of compounds that we're going to focus in on now. Either our ionic compounds or molecular compounds, sometimes also known as covalent compounds. And so molecular formulas, things that are made up of non-metals, same as in an ionic formula. The number will tell you each type of atom and how many. And there are different ways that we may show these. We have, for instance, the compound ethanol. We have our molecular formula. Molecular formulas show us that it is made up of, very touchy mouse. Molecular formulas show us that the compound is made up of, or each molecule is made up of 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. Sometimes you may see what we call a condensed formula. What a condensed formula does is it gives us information as to how the actual atoms are grouped together. The molecular formula doesn't give us any of that information. It just tells us how many of each type of atom. The condensed formula starts giving us clues as to how the atoms actually are attached. And you can see that when we look to the structural formula, which shows you the actual atoms, how they are arranged, and the bonds between them. We will look at these types of depictions of molecules in much greater detail towards the end of this course, towards early December probably. But again, so if we take a look at our condensed versus our structural formulas, we see, for instance, the CH3 in our condensed formula. We can see that here on this end of the molecule. There's what we would call a CH3. CH2 here in the middle, and then OH here on the end. And so our condensed formula starts leading us into the structural formula, showing us how all the atoms are arranged. And then we have a molecular model, which just shows us what all the atoms would actually look like in starting to look at their three-dimensional shape. And so you'll see if you actually count up the atoms in the condensed formula, it adds up to the same thing that the molecular formula does. We have 2 carbon atoms, C2, 1, 2, 3, 4, 5, 6 hydrogens, H6, and 1 oxygen for O. And then dimethyl ether is another example here, C2H6O. You'll notice same exact molecular formula. And again, this is something that we'll talk about a little bit more as the course goes on, but we would call these isomers because they have the same formula, but the atoms are connected completely differently. It gives these compounds completely different properties. So we can see the same molecular formula, but our condensed formula starts to show us that the atoms are arranged a little bit differently than they were in ethanol. And we can really see that in the structural formula. We have the CH3 group on the end, another CH3 group on the other end, and they're bridged by our oxygen atom in the middle. And so we can start to look at various molecular models. This isn't something that we're going to get into a lot of detail at this point in the course. Again, we'll be talking about this quite a bit more later on in the semester. But we can see things like a molecule of methane, CH4. We just have different ways to depict that, different ways to show what methane might look like. And each of those ways we have of looking at it will serve a different purpose depending on maybe what aspect of methane we might be looking at. We're going to spend some time now talking about ionic compounds. They are a major class of compounds. So remember that ionic compounds consist of ions that are atoms or groups of atoms which have a positive or a negative charge. And we'll take a look at ions in a little bit more detail in just a minute. But just know that that's what make up ionic compounds are ions, which are atoms or small molecules that have a charge associated with them. There are lots of different familiar compounds that we see and use every day are ionic compounds. A very familiar example is, like I mentioned earlier, table salt. Common table salt, NaCl, is one example of an ionic compound. And so when we see, so we have our formula NaCl. Something that's important to note here is that when we look at the formula for an ionic compound, and ionic compounds are very generically often referred to as salts. It's another thing to just keep in mind is that we use the term salt in everyday language as talking about this particular ionic compound, talking about table salt. But salt in general, from a chemical perspective and a chemical definition, is any ionic compound. And so when we look at the formula for an ionic compound, look at the formula for a salt. So in this case, our NaCl. NaCl tells us the ratio that exists in what we call an ionic lattice. I'll growl every time that happens. So here's our ionic lattice. If we were to look at salt under a really, really, really high-powered microscope, this is what we would see. we would not see individual sodium and chlorine atoms sort of locked together, you know, and sort of see one NaCl here and one NaCl here and one NaCl here. We don't see that with ionic compounds. We do see that with molecular compounds, which we'll talk about in a lot more detail later. When we're talking about molecular or covalent compounds, we do see an individual H2O over here and an individual H2O here, individual H2O here, and so on. We see individual H2O molecules floating around. In the case of ionic compounds, what we see is this lattice structure. And in this case, alternating sodium and chlorine atoms. And so we would have an alternating, here's a chlorine here and a sodium here. Chlorine and sodium, chlorine and sodium. And so our formula tells us the ratio that these atoms appear within that ionic lattice. And so it's an important distinction to make. And so we need to talk about what ions are. And this is a question that I have seen come up in Piazza in some of the discussions that have been happening there as people have been looking ahead of the material, which is great. An ion is an atom or a group of atoms with what we call a formal positive or a negative charge. And so up until now, we have talked about atoms as being electrically neutral. And so what that means, or what that's meant for us so far, is, for instance, if we are looking at a sodium atom. So we're talking about sodium, symbol Na. And so if we're talking about a sodium atom, we can look it up on the periodic table, and we see that sodium's atomic number is 11. And so a sodium atom is going to have 11 protons. It's going to have 11 plus charges in there. All right, there we go. So we've got 11 plus charges in a sodium atom, which again also means in a neutral sodium atom, we are going to have 11 electrons. And I'll just put little pluses and minuses there to help us keep track. So 11 pluses and 11 minuses cancel each other out. We have no charge left overall. For this conversation, we're not going to worry about neutrons. Neutrons come into play in the last lecture when we talked about basic atomic structure and we're talking about isotopes, then neutrons are important. For this discussion here and talking about ions and atomic charge, we don't have to worry about neutrons. Can you think of why? Take a second to think about that. Ions are charged. And so we're talking about things with charges now. Since neutrons are electrically neutral without any charge, they don't play a role in this discussion. They don't play a role in determining the charge of an atom or an ion. Now let's say that we now lose an electron. So one electron is being ejected from this sodium atom. It's still sodium. That is an important thing to note. It's still sodium. And remember last time in the atomic structure lecture, I focused in so much on saying that it's the number of protons, it's that atomic number, which determines the identity of an atom or an ion. So it's still sodium, which means it still absolutely has to have 11 protons. That's what makes it sodium. So our number of protons is not changing. But we've ditched an electron. We've lost one electron here. So now we only have 10 electrons. So we only have 10 minus charges to now counterbalance our positive charges. We have a positive charge left over. So this version of sodium has a 1 plus charge. That makes this now a sodium ion. It is not a sodium atom anymore. It is a sodium ion because it has a charge. It is no longer electrically neutral. Let's take a look at another example. Let's take a look now at chlorine. So chlorine, we look here on the periodic table. Chlorine has an atomic number of 17. And so we've got our chlorine atom with its 17 protons. A neutral chlorine atom will have 17 electrons. and for a charge that is going to balance out, no overall charge. What chlorine is going to do, and we'll talk about how to figure out what an atom is probably going to do as it forms an ion in a little bit. But what chlorine is going to do is chlorine is going to pick up one electron. It's going to gain an electron as it becomes a chlorine ion. It's still chlorine. That has not changed. Since it is still chlorine, it still has 17 protons. But now we've gained an electron. Now we've got 18 electrons in there. So we have an additional negative charge compared to our positive charges. We have one minus charge left over when we've used up, so to speak, all of our positives. So a chlorine ion has a charge of 1 minus. Now we do depict these slightly differently. In the case of the sodium ion, so an Na ion, we still write our elemental symbol, Na, but then we write it as 1 plus. That shows us that it is a sodium ion with a 1 plus charge. We do the same with our chlorine ion. Cl 1 minus. Now there is a difference technically between writing 1 plus versus 1 plus versus plus 1. This is how we depict an ion right here. 1 plus. And so ions, we write 1 plus, not plus 1. When we go on to talk about oxidation numbers later on in the class, again, in a few weeks, that won't be for a little bit, but when we talk about oxidation numbers, then we write those as plus 1. It seems like a nitpicky difference for right now, I know, but there is a difference between the two. And so just by convention, ions, we write in this format 1 plus or 1 minus, and it would depend on what the charge is for what the number is. I mean, we could have something like iron, which might form a 3 plus charge, and so we write Fe3 plus, maybe magnesium with a 2 plus charge. We might have nitrogen with its 3 minus charge, and so on. And again, we're going to look at how we determine what those charges are in a little bit. But this is how we depict them. So the elemental symbol, followed up by the charge. Now we're writing these charges as a superscript to the right. And so if we really sort of include everything that we looked at last time as well, we might have a full component or a full just amount of information. We might have something like, for instance, all of this information here, which would provide us with all the information we need to find all of the protons, neutrons, and electrons. So our protons, since it is sodium, our protons are going to equal 11. That's our atomic number. Our neutrons, in this case, would also equal 11 because we're given our mass number of 22. So remember that those are our protons plus neutrons, minus our atomic number of 11, our number of protons, to get us to our number of neutrons at 11. Now here, we're also given information regarding the charge. We're told that the charge is 1 plus. So remember that that charge tells us that we have 1 additional proton compared to our number of electrons. So in this case, we would have to have a total of 10 electrons in this particular sodium ion. Now I just bring this up just to show you that we can now depict all of the number of particles in a particular ion, in a particular isotope of that ion, or a particular ion of that isotope, sorry. And so that gives us the information that we need to find all of the number of all of the different subatomic particles in any particular ion. Positive and negative ions, of course, have their own names. If we remove an electron to form a positive charge, it's called a cation. If we add electrons and form a negatively charged ion, it's called an anion. And so those are important definitions to know. Cations have a positive charge, anions have a negative charge. So again, just sort of a depiction of what's going on. A cation will form when an atom loses one or more electrons. So here in the case of magnesium, we have a magnesium atom here, becomes a magnesium 2+ ion when it loses 2 electrons. An anion forms when an atom gains one or more electrons. And so here we have a fluorine atom plus a negatively charged electron. So we're adding an electron now, becomes a negatively charged fluoride ion. Again, we'll talk about that ide and that IDE in a little bit, but hopefully you noticed that we did not add that with our positive. This is still a magnesium ion, but this is now a fluoride ion. Start thinking about what the difference might be there, and we're going to come back to that in a little bit. And so to predict the charges of ions, so this table does a good job of showing that metals, what do you notice here about all the metals? What type of charge do all metals have? Don't worry about the number. Just think about what type of charge they have. They have a positive charge, right? And so metals, in the case of what we looked at in the last slide, like magnesium, are going to lose electrons to form cations. Whereas nonmetals are forming negative charges here. Nonmetals are going to gain electrons and form negatively charged anions. Remember how I mentioned, I think I mentioned earlier that hydrogen's a little bit funny. It's funny in where we place it on the periodic table. It's also funny in what it can form for charges. And we'll see why when we start talking in a little bit more detail. But hydrogen can either lose an electron to form a cation, or it could gain an electron to form an anion. So hydrogen is a little bit funny. It is a nonmetal, but it can form either a cation or an anion. Hydrogen has some funky little properties. And so metals form positively charged cations. Non-metals form negatively charged anions. That's very, very important. Now, in order to predict the type of charge or the number of the charge that an atom will typically form, what's going to happen is that by losing or gaining an electron, what an atom, quote, wants to do, if we think about an atom as, you know, maybe the happy little person trying to do something, an atom is going to try to attain the same number of electrons as the nearest noble gas. Noble gases, I think we touched on a little bit in the last lecture, looking at the regions of a periodic table. But noble gases are this column here, all the way over on the right. Helium, neon, argon, krypton, xenon, and radon. When we start talking more in detail about electron arrangement in a few weeks, we'll see that these electrons have what we, or sorry, these elements, these noble gases, have what we call a full valence shell. They have a full outer shell of electrons. So they're pretty stable just as is. They're not going to gain or lose any sort of electrons. Every other atom, though, every other element in the periodic table, ideally, in order to be most stable, is going to either gain or lose electrons so that it will have the same number as the noble gas closest to it. And so let's look first, let's look here at lithium. Again, we're going to forget about hydrogen for a little bit just because it's weird. It's fun. Let's look here at lithium. A lithium atom is going to have, shrink this a little bit and pull up our whiteboard side by side. This will work. So a lithium atom is going to have 3 protons. Atomic number is 3. That means a lithium atom will also have 3 electrons. Now the noble gas that is closest to lithium, the lithium here, the noble gas just before it is helium, just 1 element away on the periodic table. The next noble gas would be neon. 7 elements away, so pretty far away. So the next noble gas closest to lithium is going to be helium. And so as lithium forms an ion, it's still going to have its 3 protons. But in order for lithium to have the same number of electrons as the closest noble gas, as the same number of electrons as helium, that means it's going to have 2 electrons. So lithium is going to lose an electron in order to get the same number of electrons that helium has. So it will be left with a 1 plus charge. And if we look down the periodic table, sorry, I might have to use a different mouse for these lectures. If we look down the periodic table, so we look at sodium here, we see the same thing. The closest noble gas to sodium is neon. So it's the element before sodium. So sodium is going to want to do the same thing that lithium did. Sodium is going to want to lose 1 electron. And so it will end up with a positive 1 charge. Potassium does the same thing. Potassium loses 1 electron to get to 18, to have the same number of electrons as argon, and so on. And so all of the elements in this first column, all of our alkali metals, will lose 1 electron and form a +1 charge. If we look at our alkaline earth metals in our second column, it's the same thing, but now, for instance, looking at magnesium, the closest noble gas is still neon, the same as it was for sodium. But now, in order to get to the number of electrons that neon has, magnesium has to lose 2. Magnesium starts with 12. So we have magnesium atom here with its 12 protons and 12 electrons. But then to form an ion, it's still magnesium, still 12 protons, but now it's got to lose 2 electrons to have the same number of electrons that neon has. So magnesium ends up with a 2 plus charge. We're going to skip our transition metals here in the middle for just a second. We're not going to worry about those right now. But we come over to our group 3 metals. So something like aluminum. Once again, the closest noble gas to aluminum is neon. And so aluminum needs to lose 3 electrons in order to attain that charge. And so all of the metals here in group 3 will tend to form charges of +3. This row here, or this column with carbon and silicon and so forth, this is where things start to get a little bit funky. The closest noble gas to carbon is either neon or helium. So carbon could either lose 4 and form a +4 charge, or gain 4 and form a -4 charge. Neither of those things are really easy for carbon to do. Both of those are going to take a lot of energy. So carbon's not going to tend to do either of those things. Carbon, instead of losing electrons to become stable, is going to tend to share its electrons in what we call a covalent bond rather than an ionic bond. And we'll talk more about those later. So we're going to sort of just skip that row for now in our discussion of ions. But now we come over to our group 5. Our group 5 non-metals are going to tend to gain 3 electrons. So if we look at nitrogen, now our closest noble gas to nitrogen is neon. In order to get to the same number of electrons that neon has, nitrogen has to gain 3 electrons. So now nitrogen's gained 3 negative charges in comparison to what it had. And so nitrogen is going to form a -3. Or sorry, a 3-. So nitrogen, starting with its 7 protons, 7 electrons, compared to a nitrogen ion, still 7 protons, but now 10 electrons. So a 3-. And likewise, oxygen, and the entire column for oxygen. Those are all going to tend to gain 2 electrons and form a 2- charge. And then our halogens, fluorine, chlorine, bromine, and iodine, and so on, are going to tend to gain 1 electron to form -1s. Now, if we look down here, so we have to remember our differentiation between metals and nonmetals. So tin, antimony, lead, bismuth, polonium. Those are all metals. And so they're going to tend to lose electrons to form cations, which bring us into now our transition metals. For reasons that we will get into when we start discussing electron arrangements more in a few weeks, the transition metals are not nearly as predictable when it comes to how many electrons they're going to lose. There's a lot of variation there due to how the electrons are arranged around the nucleus of transition metals. And so we can't simply look at where they are in the table to determine what the charge is going to be. We have to get other clues from how we name those compounds. And so that's going to come into play for us in a little bit when we start talking about naming in a lot of detail. And so for now, just know that you can't necessarily just look at the position in the periodic table to determine the charge. And this even simplifies it quite a bit. Chromium, for instance, if I remember off the top of my head, I mean, chromium, it's most commonly can be +2 or +3. But chromium could also form, I think, a +4 or a +6, maybe even a +5. Lots of different variations that chromium could potentially have. And so we can't just use the table to predict our charges on transition metals. Well, again, we'll talk about that in some more detail in a little bit. And so the names of monatomic ions, hopefully, again, in a few slides ago, you started to key in on this when I mentioned it. But when we're naming polyatomic ions, when we're naming ions in general, if it's a cation, we don't change the name of it at all. We just take the name of the element and follow it up with the word ion, and that's it. And so a sodium with a 1+, that's now just a sodium ion, and that's just how we name it. Anions, on the other hand, we take off the end of the name of the element and we add IDE onto the end of it. And so chlorine with a 1- is now a chloride ion, and so on. And so if we look at really any negative ion, here's our example of nitrogen here. So we're going to name a nitrogen ion. So here we have a nitrogen atom over here. Now over here we have a nitride ion. And so that tells us that it's a nitrogen with a -3 charge, and so forth. Oxygen, it's going to become oxide. Something like bromine, it's going to become bromide, and so forth. So any of our non-metals that are going to form those ions, that's how we're going to name them. Nitride, phosphide, oxide, sulfide, selenide, fluoride, chloride, bromide, and iodide, and so forth. And so, like I said, for when we're talking about the main group elements, our group 1 and 2, and then our non-metals, all metal ions, we simply put the word ion at the end of it. So a sodium ion, barium ion, aluminum ion, and so forth. For the transition elements, now is when we have to use something to indicate what the charge is going to be. Because again, I can tell you, I can say sodium ion, and you know from sodium's position in the periodic table, it's going to form a +1. Magnesium ion, its position in the periodic table tells you it has to be a +2. We don't have that same benefit with our transition metals in the middle because they could be all over the place. And so we use clues in the name, or we use the name of it to tell us what the charge is. And that's what these Roman numerals here are. If you're not familiar with the Roman numerals, get familiar with them, because we will be using them for naming our transition metal ions. And so here we have copper with a 1 for a Roman numeral. So a copper 1 ion means that we're talking about a copper ion with a 1+ charge. Copper 2 ion is a copper ion with a 2+ charge, and so on. If we were talking about iron, iron can form 2 different ions fairly easily. You could either form a 2+ or a 3+. And so here we have an iron 2 ion or an iron 3 ion. Chromium, like I said, could form a whole bunch of different ions. Chromium can actually form a 7+. And so we would just call this chromium 7 ion. And that tells us what the charge is. And so since chromium is one of our transition metals, again, we can't just say chromium ion. Doesn't tell us what the charge is going to be because those transition metals can be all over the place. But now we have all the information we need. Chromium 7 tells us it's going to be chromium ion with a 7+ charge. So we need that additional information when it comes to our transition metals. And just to recap, remember with our nonmetals, and here's the names of all of them written out for you, we just add IDE on the end. I think the only ones that I didn't list off just a couple minutes ago were either tellurium, which becomes telluride, selenium becomes selenide, or hydrogen, which could also form an anion, becomes hydride. Polyatomic ions now. So what we've been talking about so far are monatomic ions. As the name implies, monatomic means that it's an ion made up of just one atom. So a sodium ion. We have one sodium atom that became an ion. A chloride ion, one chlorine atom that became an ion. Polyatomic ions now are groups of atoms that also form an ion. Typically, polyatomic ions are going to be nonmetals bonded covalently together that have a charge associated with them. And so an example, perhaps, and we're going to see a whole bunch of examples here in just a minute, but an example would be something like the nitrate ion, NO3, which has a -1 charge. Now, what this means is that we have a nitrogen atom connected to 3 different oxygen atoms, and this whole grouping together, this whole thing all together has a 1- charge associated with it. That's a polyatomic ion. It's this molecule here, this NO3 molecule with an overall charge. It's very important to note that this is what's happening. It's this whole thing, this whole molecule, this whole NO3 that all has a charge associated with it. That visualization and that understanding of what a polyatomic ion really is going to be pretty important for us as we move on. And so I always like to show that visualization of what a polyatomic ion really would look like. So this list here, this is another case of memorize them. You've got to know these. You have to be able to have these memorized. And so you've got to know the names, formulas, and the charges. So you've got to know, for instance, ammonium is NH4 with a +1 charge. Peroxide is O2 with a 2- charge. Acetate, CH3COO. You may also see this written as C2H3O2, same thing. Again, just our difference between a condensed versus a molecular formula. But acetate has that formula with a -1. Carbonate, CO3 with a 2-, and so forth. It's just going to become very important for us as we move on through the course that if you see SO4 together in a compound, that you're able to immediately recognize that SO4 is sulfate, and that's the name of it, which will be important when we start naming things in a few minutes. But also that it has a 2- charge. Also, just the recognition, though, that it is a polyatomic ion, which means it's more than likely going to stay together. That's going to become key for us when we start talking about chemical equations in probably next week, I think, maybe early or late next week. But when we start talking about chemical equations and the fact that atoms and compounds actually are going to break up and then come together in new ratios, in new ways, polyatomic ions won't break up. And so it's going to become just so key for you to recognize, if I see MnO4, that's a polyatomic ion that's going to stay together. And so that's going to be real important for us to recognize as we move on through the course. And so this is a case where these are just simply things that you have to memorize. I would recommend using flashcards for these, and I would use color-coded flashcards. What I would do is I would have the name on one side, and I would have the formula on the other. And then depending on how you do it, if you get real fancy, you can get different colored cards, different colored index cards, or just use different colored highlighters, however you want to do it. But assign each charge a different color. Color coding flashcards like that just gives another dimension to using flashcards to study. And so you might, for instance, all of your -1s might be green. And that's going to help key you in later on. You might not remember, for instance, that chlorate is a -1, but you might literally picture that card in your head and say to yourself, oh, chlorate was one of my green cards. Greens are -1. And so it just adds that extra dimension to using flashcards as a study tool if you color code like that. But these are definitely something that you will want to memorize. You will be doing yourself a huge, huge, huge favor if you have these memorized. There are absolutely more polyatomic ions than these. These are the ones that we might run into most often. And so these are ones that I would consider to be the ones to really memorize, the ones that are on this chart. So, okay, let's see how we're going to now put things together. And so an ionic compound being made up of ions will come together in such a way that the compound overall is going to be neutral. The compound overall is not going to have a charge. And so let's look at some ways that can happen. So we talked about how we can predict the charge by using the periodic table. We look to see where the atom is located in the table to see if it's going to be a +1, a +2, a -3, whatever it might be. So we're going to predict that charge by using the table. And then using the charge of two different ions that come together, we're going to look at how many of each of those we need in order for the whole overall compound to have a neutral charge, for the pluses to now cancel out our minuses. And so, okay, I'll come back, sorry, I'll come back to those. I just want to see what was coming up. Let's look at a couple examples of that. And so let's say, for instance, that we have, let's go back to our example of NaCl. Let's blow this up a little bit so we can see what's going on. So our NaCl example that we used earlier. So we use our periodic table to say that sodium, a sodium ion, is going to have a charge of +1. And a chloride ion is going to have a charge of -1. And so now let's just think about that. Each sodium comes with a 1+. Each chloride comes with a 1-. And so we ask ourselves, how many of each of those do I need for the pluses to balance out our minuses? Turns out in this case, I just need one of each. Each chloride, each negatively charged chloride will cancel out, will balance out each positively charged sodium. So one of each leads me to a neutral compound. Another way to look at it is if we just look at how things are set up here. So we have our positives and we have our negatives. If we look and see, okay, do our pluses cancel out our minuses? We see now that with just one of each, our pluses do in fact simply cancel out our minuses. So there's our chemical formula. Let's say instead of sodium, let's say we have magnesium. We'll stick with chloride. So now we've got magnesium with its 2+ and chloride rather with its 1-. We can see now that we're going to need 2 chloride ions for every 1 magnesium ion that we have. And so this means that we're going to have a formula of MgCl2. That's what our subscript here tells us, is that we need 2 chloride ions for every 1 magnesium. Now there is an understood 1 here, just like there are understood 1s here and here. We just don't write those in when the number is 1. It's just understood that there is a 1 there, but we just don't typically write it. And so now we have our formula for magnesium chloride, 1 magnesium ion to 2 chloride ions. Again, another way to look at that is if we look over here at our pluses and minuses, we can ask ourselves, do our pluses cancel out our minuses? And the answer right now is no. Our pluses don't balance out our minuses. What do we need more of? We need more negative charges. So let's put another chloride in there. Each chloride comes with a 1 minus. Now, our pluses do balance out our minuses. We have 2 pluses, and we have a total of 2 minuses. We have 1 magnesium, and we have 2 chlorides for our 2 chlorides. Let's look at a slightly harder example. Aluminum. We look up on our periodic table, and we see that aluminum has a 3+ charge. Oxide, our oxygen ion, has a 2- charge. So again, we're going to hit the same approach. How many of each of these do we need in order for our pluses to balance out our minuses? And so there's a couple ways to approach it. One is, I mean, they're the same ways that we've been looking at. We just have more complicated numbers now. But one is to sort of think of that least common multiple. We can see that our least common multiple between 3 and 2 is 6. How many 3s do we need to get to 6? We need 2. How many of our 2s do we need to get to 6? We need 3. So we get Al2O3. We can also look at it with our pluses balancing out our minuses like we've looked at. Right now, we have more pluses than we have minuses. And so we can see that we need more negative charges. We put another oxygen in here. Each oxygen has a 2 minus. Now we have 4 minuses and we have 3 pluses. Now we have more minuses. We're going to need more positive charges. So we put another aluminum in. Each aluminum comes with a 3+. Now we have more pluses than we have minuses. We're going to need another set of minus charges. There's our 2 minus. So now we have a total of 6 pluses and a total of 6 minuses. And we did that by having 2 aluminums and 3 oxygens. And so when you're coming up with an ionic formula, that's the name of the game. How many of each of these do we need in order for our pluses to balance out our minuses, so we're left over with a neutral compound overall? And that's all this is talking about here. In the case of transition metals, it's no different. We're still looking for our pluses to balance out our minuses. And we'll talk about the naming and how we can see that in just a little bit of which charge we might be working with. Another thing that you can use is what we call the crossover rule. Sometimes I hesitate to point this out, and we'll see why, but I'll go ahead and talk about it here. So let's look at our previous example. We had aluminum with our 3+. We had oxygen with our 2-. The charge on 1 can become the subscript. So, sorry. Let's go back and do that again. B. Okay, there we go. There's our example. The charge on 1 can become the subscript on the other. So Al2O3. This will always work. The reason I hesitate to bring it up is when we're crafting an ionic formula, we always want the lowest whole number ratio. So let's say we're looking at our formula perhaps for barium oxide. So we can see, again, just from looking at this, that we only need 1 of each for our pluses to balance out our negatives. All right, one barium with its 2 plus, one oxide with its 2 minus, we get BaO. If we do the crossover rule, then that's going to lead us first to something that looks like this. That's okay if you write that to begin with, as long as you recognize that it's an intermediate step, and from there, you would reduce it down to BaO. The same way that if you were in a math class, and you came up with an answer of 4/8, you're going to reduce that down to 1/2. Same idea. And so if it's an ionic formula, we're always going to reduce it down to the lowest whole number ratio. Always, always, always. When we look at covalent molecular compounds in a little bit, that's not always going to be the case. We won't always reduce them down. But for ionic substances, we're going to reduce to our lowest whole number ratio every single time. And so this also applies, as our slide says here, to polyatomic ions as well. With polyatomic ions, we will use parentheses if we need to. And so looking at an example, let's say we have a simple example first of maybe sodium nitrate. So sodium, we look up nitrate, which is NO3 with a 1 minus. Again, we see that we need just one of each of those for our pluses to balance out our minuses. And so our formula is simply going to be NaNO3. Let's say we're looking at sodium carbonate. Carbonate has a 2 minus charge. So now we need 2 sodiums to balance that out. So we get Na2CO3. Let's say we need more than one of the polyatomic ion in order for things to cancel out, though. Let's say we're looking perhaps at calcium nitrate. Sorry, Ca is a 2 plus, Professor Staples. Hopefully somebody caught that. So calcium with its 2 plus charge, we find that from the periodic table. Sorry, we're working with nitrate. NO3 has its 1 minus charge. And so we're going to need 2 nitrates in this chemical formula. And so we have to indicate that 2 by now putting parentheses around our nitrate. Again, remember when I wrote this out earlier to show what nitrate looks like? So we have to put our parentheses around it to show that this is what we're actually talking about, is 2 of this entire thing. It's 2 NO3s that are all stuck together. And so that parenthesis and the 2 indicates that for us, that we have 2 big NO3 molecules all stuck together. So anytime you have more than one of your polyatomic, you will always use parentheses. Magnesium hydroxide, Mg with its 2 plus and OH with its 1 minus. We're going to write that as Mg OH2. Absolutely have to do that. So parentheses whenever it's more than one of your polyatomic ions in your chemical formula. And these are just some examples here. So we've already looked at some examples. And so sodium with its 1 plus, sulfide with its 2 minus, Na2S. So the 1 for a subscript is understood, and we just omit that. Practice some of these. So again, this is where I would pause the video and practice them. So come up with them one at a time. So sodium and bromine, pause the video here, come up with the ionic formula for that pair. NABR. Pause the video again, come up with your formula for sodium and oxygen. Hopefully you got Na2O. Pause to work on the formula for aluminum and chlorine. AlCl3. Barium and chlorine. BaCl2. Aluminum and oxygen. Al2O3. And finally, magnesium and oxygen, MgO. And now just some practice with some polyatomics. So come up with aluminum and sulfate. Hopefully you've got Al2, parentheses, SO4, 3. Magnesium and hydroxide. Mg, parentheses, OH2. Potassium and acetate. K, CH3CO2. We don't need parentheses here because we only needed one acetate. Finally, calcium and nitrate. Ca, parentheses, NO3, 2. Let's just take a minute to talk about some of the properties of ionic compounds. And so remembering that what's going on here is we've got something that's positively charged. In this case, we're looking at lithium fluoride. So we have a lithium positively charged ion, a fluoride negatively charged ion. They're held together by electrostatic forces. Electrostatic is just a fancy way of saying pluses and minuses. So our pluses and minuses are going to be attracted and come together. So our ionic compounds are held together by these forces. Electrostatic forces are governed by something we call Coulomb's law. Coulomb's law is not, we're not going to work with any calculations with Coulomb's law for this class. Those of you taking physics will definitely be working with Coulomb's law a little bit. We're just using it to demonstrate the force of attraction that's holding ions together in an ionic compound. If we look at some of the factors involved, we have the charges of the compounds up here in the numerator and the distance between them down here in the denominator. And so the force of attraction of the ions is directly proportional to the charges of the ions, and it's inversely proportional to the distance between the two ions. And so what that means for us, just move on to here, is if we have, what do I want to say here really? Let's just come back to these, come back to our formula. And so it means that if we're talking about, if everything else is equal, if we're talking about a compound that has a plus charge and a compound with a negative charge, or a compound with a 2 plus and a 2 plus, that compound with the 2 plus and the 2 plus, maybe magnesium oxide, is going to have a stronger force of attraction. Those ions are going to be held together more forcefully because there are higher charges involved. Likewise, the distance. If we're talking about two different compounds that have equal charges, so two different compounds that are both +1 and -1 combinations, the one that is made up of larger ions will have a greater distance between the ions themselves. So smaller ions here, larger ions like this. So the larger ions have a greater distance there. So there'll be a less force of attraction. There'll be a lesser force of attraction holding them together. And that will govern some of the properties of ionic compounds. And so here we see an example of NaCl versus magnesium oxide, both roughly the same size, more or less. But NaCl made up of a +1 and a -1 will be held together more loosely than magnesium oxide with a +2 and a -2, and we see that reflected in the melting point. Since NaCl is held together more loosely, it melts at a much lower temperature than magnesium oxide does. So that's just something to note as we move forward. Okay, let's talk about naming compounds then. Take a breather if you need. Pause if you need to, absolutely. I'm gonna take a little water myself. Okay, so naming ionic compounds. Cation always comes first. That's just the rule when it comes to naming. We always put the cation first, anion second. And then you just use the names of the ions. And so when we were looking at some of our examples earlier, we took a look at, for instance, NaCl. Our name for a sodium ion was simply sodium. Our name for our chlorine ion was chloride. So there's our name for that compound. It's just sodium chloride. MgO. Magnesium oxide, and so on. Al2S3. It's just aluminum sulfide. And so when we're talking about what we call a binary monatomic ionic compound, so binary, just two atoms or two ions. Monatomic, they're both made up of monatomic, both ions are monatomic. You just put them together like that. And that's really all there is to it. When it comes to our transition metals now is when we need to add a little bit more into the name. And so when we look at any of these, for instance, in this example, these examples here, if we were to go the other way, if I was to give you the name, if I was just to tell you the name sodium chloride, then okay, we look for sodium on the periodic table. We know that sodium is a 1+. We look at chlorine on the periodic table. We know that chlorine has to be a 1-. And so we're going to come up with our formula of NaCl. And so on. If we're looking perhaps at lithium nitride, so I give you the name lithium nitride. You look up and you see that lithium is a 1+ on the periodic table. Nitride, sorry, is going to be a 3-. And so we know that our formula has to be Li3N. Let's look at what happens when it's a transition metal, though. If I just give you the name iron oxide, the oxide's easy enough. We look on the periodic table and we see that oxide is going to have a charge of 2-. But now iron is in that region that we don't really know, that region where we can't really predict things. So here's iron, right here, smack dab in the middle of our transition elements. We cannot use the periodic table to know what the charge on iron is going to be. And so you don't know what this charge here, you don't know what this charge, what this number here is going to be if I just tell you that it's iron oxide. We need more information in the name now when it comes to a transition element. And so I need to tell you, in the case of iron, that it's either iron 2 oxide or iron 3 oxide. Iron 2 oxide means that we're dealing with iron with a 2+ charge, and our oxide with its 2-. So a formula of FeO. Iron 3 oxide, as you would suspect, charge of 3+, oxide with a 2-. So now we have a formula of Fe2O3. So we need that information in there when it's a transition element. And so anytime you're working with a transition element, anytime we're talking about any of these transition elements in the middle, or in fact, our larger metals down in this region, especially tin and lead we'll run into quite a bit. So anytime you're working with any of these metals here, you absolutely must include the charge as part of the name. You have to. If you do not, it is incorrect. For this reason up above. If you just write iron oxide, I've got no idea which of these iron compounds you're actually talking about. And these are very different compounds, which will have very different properties. And so if it's a transition metal, we absolutely have to list the charge as part of the name. That's part of the naming rules. So an example here, we're working with chromium, either chromium 3, telling us it's a 3+ charge, or chromium 6 with a 6+ charge. Same exact idea. And so we might have maybe chromium 3, fluoride. And so our formula would end up, so it's chromium with a 3 plus and fluoride with a 1 minus. We would have CrF3, or maybe chromium 6 chloride is then going to be CrCl6. So we have to have that information when we're talking about a transition metal. And so this just goes over some of that naming. So again, iron 3 oxide, because we're dealing with iron with its 3 plus charge. So just some examples here. So work through these, try to figure these out if you can. Should be able to, given everything we've talked about. If, however, let's just go back to the transition metals really quickly. If we are dealing with silver, cadmium, or zinc, those are cases where you don't actually need the Roman numerals. Zinc and cadmium will only ever be a +2. Silver will only ever be a +1. And so you might very well just have the name zinc chloride. We know that zinc will only ever be a +2. Likewise, maybe we've got maybe silver chloride, so AgCl. Silver will only ever be a +1, so we can just go with the name silver chloride. Well, those are the only exceptions when it comes to transition metals: silver, cadmium, or zinc. The rest of the time, you will need your Roman numerals there. It's just some examples here. I would encourage you to work through these. If you want, feel free to send me an email with what you came up with for names, and we will talk about those. We'll come back to molecular compounds in just a minute. Just have a few more things to talk about here. Naming when we're talking about polyatomic ions is even simpler. So let's say we have the formula Na2CO3. We know that's a sodium ion. And this is why it's so important to be able to recognize your polyatomic ions, because we know that CO3 is carbonate. And that is simply the name of that ion. So the name of this compound is sodium carbonate. Maybe we have Mg NO3 2. It's going to be just magnesium nitrate. Fe, this is actually a good example. Let me do this one by itself. Fe, see FePO4. We need to come up with a name for this. What you can do here, and you would also do this if it were a monatomic as opposed to a polyatomic. But if you have to come up with the name for a transition metal, for a compound with a transition metal, then you have to use other information in that compound to figure out what the charge is going to be on that transition metal. So here, again, we don't necessarily know what Fe is, if this is maybe a +2 or a +3. We're going to use our other information. We're going to use the fact that it's here with PO4. It's here with phosphate. We know that PO4 from our polyatomic ions list has a charge of 3-. We also know that there's only one of each when we look at our formula here. There's one Fe and one PO4. That tells us that the charge on this iron in this compound, the charge on this iron has to be 3+. And so we come up with a name of iron 3 phosphate. So when you're naming the transition metal compounds, or when you're naming compounds with transition metals, you may have to use other information in there to figure out the charge. Let's look at a monatomic example. Cr2O7. Sorry, that was messy. That's better. So Cr2O7. And we know our charge on oxygen is 2-. We can also see here that we have 7 2- charges. So a total minus of 14. In the case of chromium, we don't know what the charge is yet, but we know that we only have 2 of them, and it has to equal plus 14. So that tells us that X here, the charge on chromium, has to be a 7 plus. And so that would lead us to chromium 7 oxide. Done. So the last thing to talk about in today's lecture is to look at a naming of molecular compounds. So far we focused on our naming of ionic compounds. And so how are we going to name things that are made up of a metal and a non-metal, or a metal and a polyatomic ion? Now we're going to look at how we name compounds that are bonded covalently or are molecular compounds. And so when we look, for instance, at nitrogen and oxygen. So nitrogen and oxygen here, 2 non-metals. Let me back up. When we look at maybe magnesium and oxygen, we know magnesium is going to be a +2. That's just what it's going to do. Oxygen is going to be a -2. And so the only way those are going to come together is as MgO. It's just what they have to do because of their charges, and they're coming together ionically. Nitrogen and oxygen, when things are coming together covalently to form a compound, there are a lot more options for how they're going to come together. Nitrogen and oxygen could come together as NO, NO2, N2O2, N2O4, N2O5, and I mean so on. There are multiple ways. Oh, sorry, did it again. Here we go. They could come together in multiple ways in order to form compounds. And so our name, when it comes to a molecular compound, has to indicate how many of each element we have in there. And so now we're going to start to use these prefixes. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. That specifies how many of each atom that we actually have. And then we're going to put that in front of each element in the compound. The only exception, we'll come back, is if it's one, if we have one atom and it's the first in the formula, then we don't include the mono. We can leave that off. In all other cases, though, we're going to write how many of each we have. And so here in our first example, we have 1 of each. So we're going to leave off the mono for nitrogen because it's the first element listed, but we're going to have nitrogen monoxide, nitrogen dioxide, dinitrogen dioxide, dinitrogen tetroxide, and finally dinitrogen pentoxide. And so you will always have to do this when we're talking about a compound with 2 nonmetals. I'm sorry, I'm just sort of going forward, just some examples here that you can also work through. So anytime that it is 2 nonmetals coming together, you always have to use these prefixes. Do not use these prefixes if it's ionic. And so in our case that we were looking at earlier of maybe we've got sodium oxide. So Na2O. This is an ionic compound. There we go. This is an ionic compound, not molecular, so we do not use the prefixes here. This is absolutely sodium oxide. hesitate to even write this, but I'm going to do this and hopefully make it very clear. This is wrong. Do not write disodium oxide. Do not include these prefixes if it is an ionic compound. Hopefully that's clear. So you will only ever use these prefixes when you are dealing with two non-metals coming together. If you use those prefixes for an ionic compound, a metal and a non-metal, it is wrong and it will be labeled as wrong. You will not get, if you're talking practical purposes of homework or test, you will get that answer wrong. It is not correct. So always use these prefixes if it is two non-metals. Just look real quick at one of the resources you have when it comes to naming. If we look in our Unit 1 materials, so I know there's a lot of naming rules there that we just sort of went through quickly. One of your resources, or some of the resources that you have, just remember that you have, sorry, I thought I had those on here, but some of the practice. There we go, that's what I was looking for. Your formulas and naming practice, that will get you used to using some of these rules where the rules are appropriate. And so I would definitely work on some of those practice problems, because the more of these that you see, the more you'll get used to what naming convention to use when. So, okay, that is all for today. That is a lot of information. I'll leave you with the periodic table, just as it's glorious and it's beautiful. But we covered a lot today. We covered how ions form, what ions are, how ions are going to come together and in what ratios. And then we talked about how we're going to name things using several different naming conventions. It's quite a bit of information. Take some time to digest it all, work through some of the practice, hit each other up on Piazza, make sure that you're making use of that. Piazza is a great tool. If you haven't already, be sure to read some of the emails that I sent out. And if you have any questions, feel free to let me know. Email me at any point, and hopefully I can help you out. And in the meantime, good luck. Thank you.